Bismillahirrahmanirrahim. Assalamu alaikum, dear students. I am Arif and I welcome you all to lecture number 35 on the subject of computer organization and assembly language programming. The title of today's session is Arithmetic Instructions Part 1. Well, this slide shows today's agenda. We will start with a quick recap of x86-64 register set and its related programming toolchain. Then I will describe the major categories of x86-64 instructions. And out of these categories today we will discuss some very basic but important arithmetic instructions like add with carry, subtract with borrow, increment, decrement, negate, compare, and these three instructions are used to clear set and complement the carry flag. After describing the working of these instructions, we will move on to a Linux terminal to practically see using the GNU debugger, our favorite, the working of all these instructions in true sense. Okay, so first a quick recap. Well, this slide shows the register set of x86-64 microprocessor. First of all, we have the 16 64-bit general purpose registers named R0, R1 to R15. For backward compatibility of programs written for the 8086, 8286 and 8386 processors, Intel has used a special naming convention using which an assembly programmer can access the lower 8 bits or the 16 bits or maybe the lower 32 bits of these 64-bit general purpose registers. And we have talked about these in detail in our previous session. After this general purpose register, we have this R flag registers, 64-bit R flag register. And out of these different flags, 6 are of our interest in today's session, and they are first of all the carry flag. This carry flag holds the carry out after addition or the borrow in after subtraction and is used to identify an unsigned overflow. And a related flag is this overflow flag, which holds the exclusive OR of the carry in and carry out of the most significant bit of the result. And this overflow flag is used to identify a signed overflow. So carry flag for unsigned overflow and overflow flag for signed overflow. Anyway, then we have the parity flag, which is set if the count of 1 bits in the result are even. Then we have the auxiliary flag, which holds the carry out after addition or the borrow in after subtraction between bit position 3 and 4 of the result. Then we have the 0 flag, which is set to 1 if the result of an arithmetic or logic operation is 0. And finally, this is a sign flag, which holds the most significant bit of the result after an arithmetic or logic operation. Okay, enough for the flags register. As today we are going to discuss just these 6 flags. Than this we have the 6 segment registers: code segment, data segment, stack segment, extra segment, FS and GS. We normally don't use them much in flat 64-bit linear memory addressing space. Then we have these 8 80-bit floating point registers, namely ST0 to ST7, organized in a stack fashion. The 64-bit instruction pointer, RIP, which holds the address of the next instruction to be executed. And finally, over here we have 16 128 256 or 512-bit SSE or streaming single instruction multiple data stream extension registers, namely XMM, YMM and ZMM respectively. Excuse me. Well, as far as the memory is concerned, here is the linear view of the main memory. As I've already said in the previous session, to save transistors on chip, today's CPU use a 40-bit address instead of 64 bits. Thus, the Physical memory is restricted up to 2 raised to the power 40 bytes or 1 TB byte. And please don't confuse this with the logical memory, which is 131 TB byte, having an address of 48 bits. Well, of course, for the details regarding the x86-64 programming model, if you are not new to this and you have not watched my video lectures 28 and 29, I strongly recommend that you should see those two lectures, 28 and 29, and then fall back to this. Okay, and once again, this slide summarizes the tool chain which we have discussed in detail in lecture number 30. The structure of x86-64 assembly file having the section .data, section .bss and section .text is shown in this file with the name of first.nesum. We use the net-wide assembler nesum to assemble this source file and generate the object file named first.o in ELF64 format. Then we link using the Linux linker LD, and this file first.o is linked with the standard C library, and the generated output file is with the name of myexe, and this is the command which do the same task. And finally, we load and execute this executable inside the memory. And of course, this is the general layout of the logical address space of a process. You can see the 48-bit address space. Okay, dear students, this slide shows the main categories of x86 instructions that we are going to study in the remaining part of this course, inshallah. We are done with the data transfer instruction, almost done. Just these floating point push and pop are left, I think. And today we are going to start with the arithmetic instructions, and we will finish them in next session, inshallah. The other categories are bit manipulation instructions that include logical and bit shifting operations, control transfer instructions that includes the unconditional and conditional jumps, as well as the procedure calls. And then we have the string manipulation, floating point arithmetic, IO, and some miscellaneous instructions. Okay, so this is the summary and the quick recap. And let us start with some basic integer arithmetic instructions today. Okay, dear students, the first arithmetic instruction that we are going to discuss is the add instruction. Well, this add instruction is a 2-operand instruction with first operand as the destination if you are using the Intel syntax. Well, the destination operand can be a register or a memory location, while this source operand can be a register or a memory location as well as an immediate value. And of course, when an immediate value is used as an operand over here, it is sign extended to the length or the size of the destination operand. Well, dear students, for unsigned operands, the carry flag is set in case of overflow. And for signed operands, the overflow flag is set in case of overflow. All these 6 flags, auxiliary, carry, overflow, parity, sign, and 0, are affected by the add instruction. And please do verify once you execute the add instruction inside the debugger. And we will do that soon, inshallah. The next related instruction is the add with carry, ADC, whose behavior is quite similar to the add instruction with a minor difference. The contents of the source and destination operands are added along with the carry flag, containing the carry from the previous addition. Well, dear students, ADC instruction does not distinguish between signed and unsigned operands. So the processor evaluates the result for both data types and sets the carry flag as well as the overflow flag. And actually, the ADC instruction usage is it is usually executed as part of a multi-word addition in which an add instruction is followed by an ADC instruction. Okay, so dear students, similar to add and add with carry in x86, we have the subtract and SBB, that is subtract with borrow instruction as well. This sub instruction subtracts the destination operand from the source operand, destination minus source, while this SBB or subtract with the borrow instruction adds the source operand with the carry flag and then subtracts the result from the destination operand. Remember, in SBB, the carry flag represents borrow from the previous subtraction. Dear students, like ADC, SPB instruction also does not distinguish between signed and unsigned operands. The processor evaluates the result for both data types and sets the carry flag and overflow flag. And as far as the usage is concerned, like ADC, SPB instruction is also usually executed as part of a multi-word subtraction in which a sub instruction is followed by a SBB instruction. Okay, so now increment and decrement are x86 single operand instructions. The increment instruction adds one to the only operand while preserving the state of the carry flag. And this decrement instruction subtracts one from the only operand while preserving the state of the carry flag. And these remaining five flags are affected as per the result. Well, dear students, these two instructions are normally used to update a loop counter without disturbing the carry flag. Okay, so the next instruction we are going to study is the negate instruction, NEG, which is also a single operand instruction. This negate instruction replaces the value of its only operand with its 2's complement. The operand of negate instruction can be a register or a memory location. And after this instruction, the carry flag is always 1 unless the result is 0. The remaining flags are affected as per the result. After negate, we have the CMP or the compare instruction, which is similar to the subtract instruction. That is, it subtracts the second operand from the first operand and sets the flags. The only difference is that only the flags are updated. The result is not stored in any of the operands. Moreover, CMP instruction is normally used in conjunction with the conditional jumps or the conditional move instructions. We will see to them when we'll move on to on the discussion of the jump instructions, inshallah, in some future session. Okay, finally, these are the three zero operand instructions. The CLC clears the carry flag, STC sets the carry flag, and CMC complements the carry flag. There are other zero operand instructions as well in x86, but today I'm going to discuss just these three. After the execution of these instructions, the rest of the five flags, that is the overflow, sign, zero, auxiliary, and parity flags in the R flag register are not affected. Okay, so now is the time to move on to Linux terminal and practically understand the x86 arithmetic assembly instructions that we have studied so far. So let me move on to the terminal. Here we are. Let me give the password, and here we are. So let me show you the code file, arithmetic.nesum. Well, this is a code file which we are going to run to have very clear understanding of what we have studied on the slides. The dot data section having two variables, var1 and var2, both 64-bit variables. var1 contains 1 and var2 contains 0. We don't have the BSS section, and in the code section we have different types of instruction that add or subtract with the destination operand as a register. You can see all the destination operands are registers. Over here the destination operands are memory. Then we use the set, clear, and complement instructions. the code for add with carry, the code for subtract with borrow, increment, negate, and finally compare. So finally we exit the program gracefully. So this is the code. Let me compile and load this program and run it inside GDB. So let me do nasum -g to add the debugging symbol in the file -f elf64 arithmetic dot nasum. So this will generate the .o files. Let me link the o file arithmetic.o, and let me generate the final executable with the name of arithmetic. Okay, so this will link it with the standard C library, and finally let me load it inside the GDB in quiet mode dot / arithmetic in text user interface mode. Let us load this executable in a text user interface mode because it is more friendlier and easier to understand. So here is the program loaded inside GDB in text user interface mode. Uh, well, in lecture 31, we have already seen in detail that there are different layouts like SRC, ASM, split, and registers. Well, SRC is the default layout having two windows. You can see right now we have two windows. The source window over here, you can see in the source window you have the source code available, provided if the source assembly file is there inside the present working directory. And over here we have the command window. We want to have a view of the contents of the CPU registers as well, which we want of course right now. So let's set the layout to regs. Layout to regs, that is registers. So now we have a third window over here, which is the register window. Since right now the program is not running, so the register values are unavailable. So let me put a break at the label start. Break at the label start. So I put a break at the label start. You can observe this is the first line of the code, line number 15. We have a symbol B plus over here. So this B plus has now appeared at the first line of the assembly code after the label start. And now let me run the program by giving the command run. Okay, so that's great. You can note that the program is now running, and at the top over here, you can observe that we have the registers with the values loaded initially. In the command window, at the top left, you can see the ID of the process, which is 145191, and we are at right now underscore start symbol. Great. And over here we have the current line number L15 where we are, and the contents of the program counter PC. The address is 401000, and over here we have the RIP. Where is the RIP register? Let me increase the size a bit. Info win. Okay, fine. We have 10 lines over here in this window. Let me make it 11 by increasing the win height for registers window, that is reds, and let me increase it by 1. Okay, so now we have the E flags register and the RIP as well, so that's great. So what I wanted to say is that the PC is 401000, and you can see the RIP contains 401000. And by increasing the size of this register window, now we have the view of the E flags as well. That's great. Okay, so we have the 16 general purpose registers, RAX, RBX, RCX, and so on, and the RIP and the E flags as well. And right now only the interrupt flag is set. Fine. This hex hex value 202 means bit number 1 and bit number 448, and yes, if we start from 0, then bit number 1 and bit number 9 are set. And we have seen that bit number 1 is reserve while bit number 9 is the interrupt flag. So that is what is shown over here. Okay, so let me now run the program line by line. The instruction at line number 15 will be executed first. It is not started. Let me start it from the beginning. Yes, so this is the instruction which is going to be executed. And this instruction moves an immediate value RA01 to the RAX register. Right now RAX register is 0, so once I execute this it will contains 1. So let me do SI, and here you go, the RAX register contains 1. And this instruction add RAX to var1 is an add instruction which adds the contents of variable 1 to the RX register. Let me first examine the contents of the memory location var1, and I can do that using the examine command xg. The format is hex, and I want to display a joint word from that address, and the address is var1. Okay, so that contains 1. So var1 contains 1, rax contains 1. So once this instruction is executed, of course rax will contain 2. And you see rax contains 2. So that is great. Well, this next instruction will move an immediate value all f's to rax, and you see all f's inside rax, and all f's of course means -1. Then this instruction is going to add a value inside rax, an immediate value 1 to rax, which will become of course 0 after we execute this instruction. So let me run it, and you need to keep track of this as well, and do watch for the flag register as well. That's great. So it has become 0, and you see the E flags, the different flags are set. You can see the 0 flag is set because the result is 0. The auxiliary flag is also set because there is a carry out from the bit position 3. The parity flag is also set because the count of 1 bits in the result is 0, which is of course even. And finally the carry flag is also set because there is a carry out from the most significant bit, that is bit number 63, once we added 1 to this value. So that is great. So anyway, this instruction at address 19 is going to move the immediate value 9 to the RBX register. So RBX register will contain 9 after the execution of this instruction. Yes, it is. And this instruction is going to subtract the contents of RBX from RAX and place the result in RAX. So after this instruction executes, the RAX will contain -9. Let me execute this. So there you go. So this is -9, and this is a 2's complement of 9 inside RAX. Also do check the flags. Note the sign flag now is set because the result is negative. Okay, dear students, now these are the next 3 instructions. If let's suppose var1 contains 1 and var2 this contains 0, tell me after these 3 instructions executes what will be the contents of var2. So this instruction will move this 1 to RAX, and this instruction will move the contents of 1 to this, and then we will add this with this. So finally I think we'll be having a 3 over there. So let me do the step in once, twice, and thrice. So there you go. So var2 should have 3. Let me check out by examining ampersand var2. So there you go, you have 3. And remember, previously it was having a 0 inside it. That's great. That's great. Okay, so now these are the next 3 instructions. They are going to clear, set, and complement the carry flag. The carry flag is already cleared, so this instruction will not have any effect on that. Okay, so now set the carry flag. You will observe that the carry flag will be set. Great. and this will complement the carry flag, so the carry flag will be complemented after we execute CMC instruction. That's great. Fine. So now we are at instruction number 33. Move RAX comma 0. So these instruction will move 0 to RAX, and then it will set the carry flag. Fine. RAX contains 0, set the carry flag. The carry flag will be set to 1. You can see the carry flag is set to 1. Now there is an ADC instruction, add with carry instruction. This will add this immediate value, that is 1, along with the carry flag to the contents of RAX register, which is 0 right now. So after this instruction, the RAX register will contain, I think, 2. So let's see. Yes, RAX register contains 2. Now this is again going to set the carry flag. So the carry flag is set. And now this is going to do again add with carry RAX with 2. So this 2 will be added to the carry flag. This makes 3. This will be added to this, the contents of RAX, that is 2. So after this instruction execute, RAX register should contain 5, I think. And there you go. We have 5 over here. Oh, my dear students, in the same fashion, please verify your concepts regarding these subtract instructions as well, and the subtract with borrow instruction as well. And meanwhile, do keep track of the E flags register. Similarly, do work out with the increment and the decrement registers, very simple, and the negate instruction. And you see right now RAX contains 6, so this instruction is going to move 1 inside RAX. So 1 is there inside RAX. Now I'm going to negate the value of RAX register, and you know, once we negate that, we get a -1. And finally, this is the compare instruction. These 3 instructions are the compare instructions. First instruction will move 5 inside RAX. So there you go. We have 5 inside RAX. This will move 5, immediate value 5 inside RBX over here. There you go. We have 5 in RBX. And this is going to compare the contents of these 2 registers, RAX and RBX. And this is going to subtract it. We get 0. The result will not be stored anywhere. However, the flags will be updated. And note the 0 flag that is set after the execution of this compare instruction. Okay, so finally, these are the 3 famous instructions that we have come across in every program. They are used to exit the program gracefully. So let me press C and continue this program execution till the end. So there you go. The process 145199 exited normally. So that is great. Let us fall back to the slides. Okay, dear students, please do practice running all these arithmetic instructions with different values, and meanwhile keep track of the status flags to develop a very clear understanding as to how the x86 CPU processor executes them. In the next session, we will inshallah study the multiplication as well as the division instruction, both their unsigned and signed variants. I hope today's session was informative for you all. If you have liked it, please subscribe my YouTube channel and share it with your friends. Wish you all the best, happy learning, and Allah Hafiz.